Okay, so today I'll give an overview of a privacy solution that we implemented at Clearmatics. Kind of a good maybe precursor to the next talk as well, because I'll go into a little bit of zero knowledge proofs and what, like how they work, and give a simple conceptual examples. I'm not going to go too deeply into the math, because whenever there's a non-academic audience, it's not a good idea. But generally, yeah. So you'll get like a general idea of for real. You'll get a general idea of like what the point of this is. So it's an abstract solution. You know what? Hold on. Okay, great. Anyway, so you'll get a general idea. So this is a solution really mostly. It's not so sophisticated as like zk snarks. If you think of more different privacy solutions like Zcash. That have way more overhead. So this tries to be simple cryptographically, such that it doesn't rely on too many untested assumptions, and also performant. So you can do like your tens of thousands of transactions a second. So a little bit of background on me. I'm the lead engineer at Clearmatics. I work on the distributed systems and the crypto side of things. I'm also on the security team at the Ethereum Foundation. I help them out on like core protocol layer audits. If Ethereum gets attacked, I help them out. And Clearmatics in general, has a good sort of connection to the open source community. We try to contribute back to it. So I'm mostly a software engineer by trade, but I've always had a heavy personal interest in mathematics, crypto, and security. So hence why I'm talking about security today. And I've been heavily involved in the crypto and P2P community for years. So the motivation here for, why do we need something like this, a privacy solution? Cryptocurrencies, like the main use case up until now, and really the main use case by activity beyond 99% is, their use of digital cash. And blockchains in general overshare information hugely, right? There's no way that I can even pay buy a coffee without if I do it naively, without exposing, my entire holdings. Especially if I get paid into that account, now my salary, all my dealings, and it's bad. Not just if you want to be a criminal. Everybody always thinks, oh look, why do you need mixers and privacy on blockchains? You're just trying to hide your drug buys. Not really, right? Like, if this is actually ever going to be used for like mainstream transactions, payments, getting paid for jobs, you do need a way to delink payments. Even if it's not delinked totally, like you might still want like a regulator or an auditor or a financial institution to be able to see it. You don't want the whole world to see it though, right? And that's bad. Like I would not want to expose every single transaction that comes in and out of my bank account. And I imagine most people wouldn't want to do that either. So you're like right now in blockchains, whether you use Bitcoin or if you use Bitcoin and Ethereum, whatever, these like sort of naive blockchains. Or sort of, I guess, privacy independent ones. It's very, very easy to de-anonymize participants. Yeah, there we go. So it's quite easy. Like even if you try to go through mixes and whatever, there's no perfect solution yet. Yeah, I guess, and again, in the naive blockchains, and even if you use something like Zcash, obviously it's much better, but again, there's so much overhead in using something like that. If we were to use it for day to day, you would never be able to you would never use Zcash for paying for coffees. That's just not going to work. For some background, like one Zcash transaction takes about 30 to 50 seconds to generate. You especially try to do that on your phone, probably take like 6 hours. Stay there at this coffee shop 6 hours for your payment to generate. They're probably not going to work. But yeah, anyway, like the mixers always rely on trusted third parties. In the Bitcoin side as well, you have things like Monero, but there's problems with that. We'll go into it. So this is kind of like just a general solution, not just for normal one-to-one payments, but for general kind of delinking that you can use on any Turing-complete blockchain, or any blockchain can sort of implement the semantics. Yeah, so that's the motivation as a whole. So we use rank signatures. Why are they interesting? Here's some sort of use cases for rank signatures in general. So you can do voting, like anonymous voting. So like the background is, you have a ring of keys, so a group of keys, and you signed from one of these keys, and I can prove to you that I signed from this key from this group, but you don't know who signed exactly, right? So there's some common use cases that come to mind, which is voting. Like I want to vote for some politician or I don't know, some event, and I want to be able to vote without exposing who my vote exactly. Without getting that one-to-one correspondence between my key and a vote. So you can do that for that. You can do this for leaking secrets, which is actually why they were invented, and I'll go into that in a bit. And payments, and especially payments from group. So that's the topic of the talk. So what are leaked signatures exactly? So the concept first introduced in a paper titled "How to Leak a Secret" by the RSA authors, 2 of them. So it concerns using keys in a group instead of using them individually to prove you have a private key from the group as opposed to proving ownership of a specific key. It's like, so this is, the paper, the seminal paper that introduced them, like gave the use case to whistleblowing, for example. So if each public key in the group belongs to a government official, the official can leak some classified data proving that they are indeed a government official without outing himself or herself individually as the whistleblower, right? So if you say, look, here's this group of 10 keys, each one of these keys belongs to some government, someone in like the US government or the NSA or something, and one of these people, sees something unethical happening, but they know that if they leak it, they'll disappear, right? They'll get into an accident. They'll suicide themselves by zipping themselves up in a black bag, right? Things like that. So they don't want to expose that, but they do want to expose a secret. They want to expose this corrupt behavior happening, so they sign like a statement saying, look, I see this bad stuff happening, and I prove that I am one of these 10 individuals who would have seen this without proving exactly, without revealing exactly who I am, right? So this is a this is a type of zero knowledge proof. So the next talk will go into more depth of this, but for me, I'm only going to go into a little bit of an analogy. So a zero knowledge proof allows you to prove the knowledge of a secret, for example, without revealing anything about that secret, in loose terms. So a simple analogy that I prefer over all other analogies is that, say that I was to choose a card from a deck of cards, and I want to prove to you that it's a red card. If I just show you the card, it reveals way more than just a color. It reveals the suit, the number, whether it's Jack, King, or Queen, or like an ace, or whatever. But I don't want to do that. But I do want to prove to you that it's a red card. So as a quick analogy, if like I can prove this to you in zero knowledge in a way, if I just take my card from the deck and I put it aside, and I take the 24 black cards in the deck and I flip them up, and reveal them, and then the only things left in the deck are red cards. And if my card is on the side and there's 24 cards flipped up and there's 58 cards in the deck or whatever. Assume that there's 24 black cards and 24 red cards, then I've kind of proven to you that all the cards that are face down must be red cards, and so hence my card must be a red card, right? And so like this is, obviously you have to trust that I haven't like gamed the deck, right? Maybe I could have a deck that has 25 red cards or 25 black cards, and actually my card is actually black. But the cryptography, the analogy here works because the cryptography sort of forces us to use the correct deck, right? The cryptography is the enforcer of the deck, and through that you get that zero knowledge proof out of that, assuming you follow the protocol correctly. Then this specifically, zero knowledge proofs in rig signatures is called zero knowledge proof of set membership. Again, just like in the card example, I only reveal to you like one property out of the set of properties, meaning I only reveal to you that I have the color, like the red color of the card that I have, without revealing to you anything else. In the ring signatures, I merely reveal or prove that I have a private key in the set of keys without proving to you which one specifically it is, right? And like the way signatures work, generally if you were to use like naive ECDSA, like elliptic curve signatures or RSA signatures, without having the specific public key, you can't verify my signature, right? You need to know exactly which public key it conforms to, and once you have that key, you can provably say, look, it's actually this key, this guy signed it. But in this way, you have one of many. So this is what it looks like. I'm not going to go into it, but this is generally the math for ring signatures. And so we need there's an important piece here that we need to extend to allow it to use for payments, voting, and so on. We need to add a specific component which allows us to check if somebody has signed twice, but without revealing, which person signed twice per se. Without this, I can, if I spend from a set of public keys, and if I'm allowed to do this more than once, I can basically steal other people's money, right? Or in the voting example, I could vote infinity times, or more logically, if I have 10 people, I could vote 10 times and take away everybody else's vote, right? Because if you have 10 people, there can't be more than 10 votes. So this is really important. There's an important extension here. So which makes it useful for a specific message and ring. So the message could be like who should be president, the U.S. president in like 2016, and the ring would be like the set of the American people, right? Eligible voters. For those two specific pieces of information, I can tell whether a person has signed, a person or a key holder has signed more than once, right? So yeah, that makes it allows you to screen for anonymous voting in private transactions. So there's one more problem in the blockchain scenario where we need to give users, an easy way to derive new keys and addresses, right? Because just being able to delink payments only really kind of solves half the problem. If I want to pay you, if you have an address, and say I'm paying, I'm your employer and you're my employee, if I'm paying you, over and over, throughout the course of the year, if I only have one address for you, then it doesn't really matter if that payment is delinked from source to a destination, because I still, you can still see 12 payments of a grand were made over the year. This is clearly a salary, right? So you're leaking a lot of information by not having the ability for people to generate new addresses, but also generate new addresses without communication, right? You don't want to give your employer, or especially if it's something non-interactive, if you want to set up a direct debit to someone, you don't want to ask them for a new bank account every time you have to get the direct debit, right? So we solved this problem with a construct called stealth addresses. Stealth addresses come from Bitcoin-ish. I mean, they're just kind of really basic elliptic curve math anyway. But so instead of publishing your address, you publish a long-term master public key by which people can derive child public keys, but they derive them in such a way that they derive them in such a way that a third party cannot know which child keys belong to which master key, right? So only you can derive a child key for your payee, and a third party just sees them as random payments almost. And only one communication is needed, that pair, which is nice. So you just kind of see this as Diffie-Hellman key exchange of elliptic curves, and that's basically what it is. Yeah, so this really extends the scheme again by requiring only one communication for basically infinite address pairs. So the idea is this, right? With some, I'll skim over the maths a bit, but so the sender generates a random key pair, private key, little r, public key, big R, sends a public key to the recipient, and the recipient has a long-term key pair, A, so that's your payee. So that's in the R that your new pair is communicated with the transaction, and the derived public key, and the derived public key and private keys just use this basically like the curve math. You take a hash of the initial key, you take a hash of the recipient's public key to the power of your private key, and then hash that, and then do a hash to the curve point and multiply A by that hash, by that curve point, and that's your derived public key. And because of homomorphic or commutative properties in elliptic curve, the recipient, your payee, automatically knows that this is the derived public key, but they only know that because they have this. They only know that, they only know that because they have the public key that corresponds to this because of some elliptic curve maths. So without needing a secure communication channel per se, as long as we know each other's, as long as we know each other's like public keys. Again, like we put public keys in our contract. We can do self-address derivation by just picking some R random element from the queue in the module. And R is sent along with your transaction, so your fresh key pair is kind of like included in your transaction, and the intended recipient computes what would be their address with each new public key R that they see. And if this matches the actual address, then they can compute the corresponding private key and save that for later. Right. So this is how you the real scheme. How you would do this. You add a nonce, and then the recipient can just sort of iterate through the nonces after the secret sharing has completed. And yeah, now after we've done this setup, if I have to pay my employee, I just run this protocol, and every time I pay them, the sender, the recipient address will look completely random. So you can't tell if I'm paying my employee 12 times or if I'm paying 12 different employees one time, right? But the employee will always know because we both have the shared secret. They can scan through the blockchain and see, yes, this payment is meant for me. Let me derive the private key that corresponds to this payment. Yeah, and if you wanted to make this easy, per se on Ethereum, you have a public key registry where you just have a smart contract that just takes everybody's it's kind of it's a smart contract version of key servers, and then if you see a payment linked to one of the public key registries that is public to the world, then great, you see it. So let's go into how the actual ring signature contract works exactly. So remember, the ring signature is verified against a set of public keys rather than against one public key. So the way that the ring signature contract works would be, or ring signature payments work in general, is that, so imagine you have person one, or address one rather, this could all be the same person, it doesn't matter, but there's 3 different addresses on the network, so which all have the same amount of tokens, right? So this address 1 has 10 tokens, this address 2 has 10 tokens, and this address 3 has 10 tokens, right? And so one of these people wants to pay Alice here 10 tokens or 10 units of monetary value, whatever. So you can say that the set of addresses is your ring, right? Is your public key group, and the message is sort of this the sender, right? There, or you can just generate a unique signature, which is the block hash, but in this way, because we're assuming addresses are never used, your recipient is the message that you're signing, right? So you say, you have this ring, your message is sort of your intended recipient, and by doing it this way, say that address 1 signs to send 10 tokens to Alice, address 1 will sort of commit a public key that Alice knows the private key to into a smart contract that acts as an escrow, and the once all these other payments have put in their 10 tokens to go to somebody else, Alice knows that she is one of the intended recipients and can go in and withdraw withdraw the 10 tokens entitled to her by signing from the group of the committed keys. Yes, and proving that she is entitled to those 10 tokens. But she cannot withdraw more than once, because if she tries to do that, obviously it's detectable. This is a nice scheme as well, because it, unlike a lot of other schemes, it also hides the identity of the sender from the recipient itself, right? Because if this is our ring of keys, and Alice is one of the people withdrawing, all she knows is that her boss or her employer is one of these people, right, or one of these addresses, but she doesn't know exactly which one it is. Again, because of the way that elliptic curves work, the zero knowledge is both on the receiver side and on the sender side. So yeah, there's the tag. There's a specific sort of byproduct that is generated when you are generating these signatures, which is the tag, which is really just the it's like the hash, it's the curve point that is given by like the hash of the message and the ring, and that's always the same regardless of who signs. Well, no, sorry, that's always the same given the same signer because it's powered by the signer's private key. So if the same signer tries to withdraw twice, you will see, look, somebody tried to be evil and get more tokens that they were entitled to, but it doesn't tell you exactly who did it, right? Which is nice because even if you make a mistake and try to sign twice, like sort of your privacy still remains, but it never gets, there's no security vulnerability for anybody else. So in this way, we can build a smart contract that allows senders to deposit funds in a public key and allows recipients to retrieve this corresponding private key to the public key that was deposited, that the sender were deposited to, form a linkable ring signature, and withdraw the funds they are entitled to only once, right? And again, this is nicer, even though it's not as fancy as ZK-SNARKs or anything. It's very performant. It's if you use nicer cryptography, you can use sublinear, meaning that the signatures do not grow linearly with the number of participants. They grow sublinearly, so it's efficient. And if you have like rings of 10 people and you go through funnel your funds through multiple rings, it becomes statistically indistinguishable. So you have that nice security property, and it's very performant. I mean, this is ring signature is it's not really much more expensive to compute than a normal ECDSA signature. So the slowdown is a really constant time slowdown, meaning basically you can do thousands to tens of thousands of these ring signatures a second if you have like a mainstream server, for example. So here's sort of the stylization of what it would look like as a contract, right? Take that we did it on Ethereum. We have the senders, and so just take going back to the fact that we need a ring and a message. Take that we have a message M that is fixed for this ring specifically, and you have payer 1, payer 2, and payer 3 that all want to pay somebody 10 tokens, right? But obviously the person that they're paying could be different, or is likely different. So what they do is they take their 10 tokens and they attach, and along with the value transfer, they associate a public key to that, right? And then they submit that to the smart contract, again, which is as escrow, sort of just trustless escrow. And so you have a public key 1 goes in, and 10 goes into the smart contract, public key 2 and 10 goes into the smart contract, and so on. So if this is a 3-participant smart contracts, once it gets the 3 keys in it, it's locked. So now the funds are eligible for withdrawal once the funding stage is over. And somebody comes in and says, look, I have, with my zero knowledge proof, says I have one of the keys, one of the private keys, related to one of these 3 public keys, right? So the signature, as you can see, is over this entire ring. Yeah. So the green, white, and red. So the signature is over the entire ring. If they try to sign twice, they're rejected, but they will get their money the first time. And same the second withdrawer comes in, withdraws from the ring, takes that back. The third withdrawer comes in, withdraws from the ring, and takes that back. And as long as this can happen infinitely between these 6 participants, as long as the participant, each pair of payer-payee participants have interacted only once to share that shared secret. And the next key for the next ring can be a totally different color, but the receiver will always know, yes, I see that key is one of the derived keys from my master public key. So you have one round of communication for the setup, but infinite interaction, infinite amounts of payments later on, from then on. So the conclusion, we have a smart contract that enables us to construct ever available and incorruptible programs. The rig signatures allow us to unlink sender and recipient pairs, information theoretically and statistically. The key derivation offers a way to construct many transactions with amortized communication cost, all keys appearing random to third parties, or to parties without the shared secrets, and guarantees that the party constructing the new public key cannot construct the corresponding private key due to the security given by elliptic curves. So the long story short, if you got too distracted, the sender and recipients derive a secret. The senders use this secret and the recipient's public keys to derive new random-looking public keys. These are deposited into the smart contract along to the funds to be sent. Each recipient can derive the corresponding private key looking at the smart contract if they have the shared secret. If they don't, then obviously the payment's not for them. A ring signature is then formed over all the public keys in the contract. This ring signature is sent to the contract from a freshly derived address. The smart contract trustlessly checks that the signature verifies and then releases the funds to the appropriate signer. So I'll present a question here. Why can't you just use Monero for this? Well, there is another blockchain called Monero that uses ring signatures, but while this solution uses active ring signatures, meaning I must sign up to be in the ring and I must withdraw in the ring. This is like a conscious action. Monero takes the set of all public keys, all transactions that have ever happened, and that's the ring that you sign over, right? You pick like a subset of that, and you can do a withdrawal from that or send a payment. So the mixing capacity, you can't wait. You don't have to wait for other people to join your ring. But the big problem is that if somebody uses the Monero protocol incorrectly, they de-anonymize you, right? That's really bad. Like I don't want a protocol where if other people don't know how to follow the protocol, then I also get damaged from it, right? That's bad cryptographically. So this is one of the big issues with Monero, and then it's kind of happened over and over again. Because again, for the first year, Monero people were using ring sizes of 1, which is clearly then you're not unlinking anything if you're paying from 1 to 1 or 2, and also because of how Monero is structured, because of how the crypto Monero is structured, this is extremely unscalable because it's also unshardable. It requires you to have all public keys that have ever transacted to be on the blockchain forever. You can never compact those. You can never take them away because once you do, you unlink massive swaths of participants, or basically make them unable to spend their funds. So Monero in the long term is unusable because it can never be optimized. So that's the passive ring mix doesn't really work that well. Okay. Any questions?
I'm not sure I fully understood it, but I'll try a question. In the example you gave with the employer paying the employees,
yep.
Right now, if an employer is paying employees, it's a deposit, right? The
yep.
employees just receive the funds in their account. From my understanding of what you just said, the employee has to request the funds. Is that right?
It's not so much a request per se. It's not a request in the normal sense of request, being like you have to you request and receive approval. It's more like it's the equivalent of logging into your bank account, right? So
but that is still quite different. It's not if you wanted to replicate how employees are currently paid today. In your example, it's not replicating that. I just want to be clear that that's because the employee would then have to effectively make some form of request.
Is it not that the node scans, so the recipient wallet scans a blockchain?
Yeah.
Basically, when it detects that a payment for it has been sent, then it says, "Oh, okay, I recognize that, so I can decrypt it, whatever."
Yeah. Was my interpretation incorrect, or is that?
Yeah, I mean, like if you want to get super pedantic about it, you will have a point. But I mean, so if for example, as you said, your wallet, wallet can automatically scan the blockchain and just show you the funds that are in your wallet because they are in your wallet.
Okay.
And you can withdraw. So basically, weird technicalities aside, your smart wallet can show you a deposit as your bank account would show you a deposit, right?
Right. So the action of viewing your wallet would then make that request.
Yeah.
Fine.
Yeah, exactly.
Okay. No, I just wanted to understand whether it could be replicated.
It's not a sense of look, I must have to go in before this can actually ever go through. It's like at the moment your employer pays you, you are entitled to it automatically, right? It's it's kind of
Okay.
Yeah. So,
fine. Great. Thank you.
Any questions? Yeah.
quick question. Capital R, I guess that was a temporary address. It's not long term, right?
Yeah, so it's like all the addresses you see, at least the recipient ones are one time. So like
capital R is one time.
Yeah.
Cool.
Capital R is just a one-time public key. Yeah.
Cool. That makes sense. What would happen if the public key, the long-term master, was shared more than once? I can't quite think. I can understand why it might be, but I'm thinking.
What do you mean shared more than once?
Because you said that the long-term master, which I guess is a public key, which would be, what did you label it as? A, capital A?
Yeah, capital A.
So if you were to share capital A more than once.
So like the way that it works is really like, so the only issue is, so say that, me and you set up do a shared secret, and now I can create infinite subaddresses for you.
Sure.
The issue is not using that master public key more than once because the shared secret is a combination of my public key, or basically my private key and your public key, right? It's Diffie-Hellman in that sense. If I use your A and somebody else uses your A, the addresses will be completely different. So there's no collisions there. The only collisions is if I use your A and then I use nonce1 for your first address, and then I use nonce1 again. Obviously, that's the same address, right? So it's up to me to use same nonces.
You should use different nonces.
Yeah.
Yeah, okay, so not actually on A, so if I reshared my A for whatever reason, that's fine, but it's more about not reusing a nonce, which is just standard cryptographic,
exactly.
good practice, whatever. Cool, that makes sense. The other one was you had 3 addresses, but you said all of them had the same account, had all the same balance. And obviously it's pretty good from an anonymity perspective to have balances all the same, but they're all 10, 10, 10, 10, 10, 10, 10. But if they're not, then how is this affected?
You can't have them not the same balances, right? Because like you can, if you have like, if you're paying like 55 to someone, you can split it up into like 5 rings of 5, right? Like the protocol will automatically manage that for you. The reason you can't have, like, I deposit 5 into a ring and somebody else deposits 10, that's not, then you've lost money basically, because the ring signature only says there's one, like the ring, when you sign to withdraw, the ring signature merely proves I own one of the keys able to withdraw. It doesn't say I own one of the keys and a number able to, and this specific number, right? Because that would link the payments. So like the rings have to always have the same denomination, but you can sort of chain different rings together to do arbitrary payments.
Okay, so maybe I need to think in that one, but I'm just thinking, because obviously if it's going to be an arbitrary payment, if people want to send 2.63 and 4.54 or whatever, all of the transactions should be completely different. Yep. In theory. So I guess I'm just trying to see how do you...
So like again, So I mean, this is why you have like standard denomination rings. So again, if somebody wants to send, like 55, and then somebody else wants to send 63, like most of that can be like, 5 payments of 10 and 5 payments of 10 applies to both of those, right? And then you just have the first one is you find another ring of 5, and then the second one finds 2 rings of 5 and a ring of 3, right? So you split the payments into different rings that have the same subdenominations, but the wall sort of abstracts this for you, right?
And is it only integer payments?
Yeah. It's only obviously, because if it was floating point payments, you have an infinite set, right?
That's kind of what I was wondering.
I mean, like there's an extension to this where you can use like range proofs, which the next talk we'll talk about.
Are the addresses public? The actual balance is public. So
obviously the balance of each address is always public, but if you don't have the shared secrets, or if you don't have the master public key, you cannot group the addresses, right? So all you'll see is like there's 10,000 addresses that have various numbers in them, but I have no idea which 2 of these addresses is the same person, right?
Sure, but you can look at the balance.
But I mean, so that doesn't tell you anything, because again, like.
Oh, I guess because you could have lots of different addresses for one person. Yeah. Okay. Yeah. Cool. I get that.
Coming back slightly on the same topic, there's something pretty cool that was developed on Monero quite recently, which is called Ring City, that combines ring signatures and so-called confidential transactions that come from Bitcoin and using range proof and ring signatures actually allows to hide the amounts. So if I understood well, right now in your mix, everyone would have to send the same amount, which is visible. Yep. So did you explore a bit trying to integrate Ring City?
One of the problems with things like confidential transaction is that, like, the reason that we didn't choose it here is, well, at least not naively, is that it hides the total coinage, right? Meaning that if there's a bug, somebody can create infinite coins and you have no idea about it, right? So that's obviously not like acceptable for like banking use cases, because you don't want your bank to be like, well, you know, if there's a bug in this, the money supply is done, right? Somebody can just create infinite billions of dollars. But like in a sense, this hides the transaction amount in a sort of auxiliary way, because again, like if I want to pay you 100, but I split that into like 20 payments of 5. Sure, there's like a transaction. There's a set of transactions that perform a 100 value transfer, but you don't know how to group those because you don't have the shared secrets, right? So from a third-party perspective, the third party does not know whether I've done, you know, 2 payments of 50 to the same person, or you know, 20 payments of 5 to 20 different people, right? So only if you know the shared secrets is the amount blinded. Like to totally blind it from all perspective, always hide the total coinage, which is, you know, maybe that's acceptable sometimes, but it's a big disadvantage.
I think it might be a big disadvantage if you want to mix much more money than anyone else at a certain point in time.
Yeah, well, if you want to do that, like, if you want to do that generally, that's kind of hard to hide anyway. Like, even in Zcash, like, even in Zcash, which hides everything, hides sender, recipient, coinage, everything is hidden in Zcash. If you'd like move a fuck ton of money into the hidden, like, you know, version of the Zcash coins, and then like a fuck ton of money comes out later on, obviously it's must be some subset of that guy's payments, right?
But you can do timing analysis, which you cannot do on Monero because you have Ring City. That's why you also gain on scalability issue because you don't need to split over several mixers.
Yeah, so I guess if your coinage is always hidden and no one other than the recipient ever knows the coinage, I guess you can do that. But then it's like the fact that the total coinage is totally hidden and you can never ever reveal it is a big trade-off. Yeah, but that's a trade-off you take.
Thank you.
Okay, I'll just take 2 more questions. I saw there was someone here.
Hi, I just missed, in terms of you've got some homomorphic functions, some sort of bilinear pairing or something. How are you checking that someone signed once, that they signed at least once, and then they've signed only once? I didn't quite, the maths I didn't quite get.
I mean, so I don't. It's too hard to go to maths without like. Well, sure, actually, if you want to understand the maths, it's here. Yeah. So the tag, which is tau here, so the tau tag is always the same because it's generated based on where is it? Yeah, the tau here is always the same because it's generated through this. This is tau. This is how tau is generated. So for a certain for a certain signer, so here's the signer's private key. You take the hash. This is hash to the curve point. You message. So like, you know, the ring instantiation. Concatenate that with a set of public keys, and power that by the signer's private key, right? So only the signer can generate this tau, and it's not reversible because of discrete logarithm problem. But if he tries to sign twice, he can never change this, right? So that's because this is the signer's private key, right? If he chooses a random private key that's not on the ring, then the signature is not valid, and this proof won't hold. So this is tau. This is the tag. If you try to sign more than once, even though all these other variables, the C1s, the commitments, the T1s, these are all simulated zero-knowledge commitments. So this all changes. So the signatures looks totally random each time, but the tau always looks the same, and the tau is part of the overall protocol. So. Cool.
There's been well, we've seen a few different use cases for the technology that you presented during this. So I'm going to ask a deliberately non-technical question. Out of these different use cases that you presented, which one do you think is actually most appropriate for what you've created?
I mean, payments is good. Payments or so the stealth address isn't really relevant for payments because, you know, there's not much else. I mean, I guess you can still anonymize like other actions, but yeah, the payments and voting. I'm really into, you know, one day seeing blockchains used for voting. because I think it's just much better, more secure, verifiable than using pen and paper ballots and whatever. Just give it one of the interesting developments is like the Estonian government. If you go to their embassy and you pay like 100 quid, you give them your passport and they give you like a little smart card with an elliptic curve on it, elliptic curve key. You can take that and derive keys from that and sort of like prove, look, here's an identity I have that has been verified by the that has been verified by the Estonian embassy, and I can use this for voting, right? Like the Estonian embassy will never issue more than one key to me because they know my identity. And then we can use like trustless anonymous voting that is incorruptible. So I think actually that's a really good use case, and hopefully one day that will actually be used for governmental functions.
Thank you.
Okay, cool. We're going to have to push on through just for time's sake. I'll see if I can get a bit of aircon going in here as well, just to cool things down, because there's a lot of people and not too much